that's it. That's it for the Hedera SDK section of this tutorial. And in the final half an hour, I think we can go over the Hardhat and Ethers way of going through it. So if you've been following along with the tutorials, I'm going to back to the GitHub repo, right? Just go in the docs folder, move over to Hardhat. All right, so Hardhat is a development framework specific, helpful for smart contract development. So very common stack among developers in EVM-compatible networks, and you can use it with minimal effort or configuration with the Hedera network as well. So let's move on to setting up the project. So let's go to the folder for this, Hardhat, within the repo, and then npm install. You get the prerequisites. Now let's close all of this and open up Hardhat, right? So this is the Hardhat project, and we have a config file, and we also have a package.json file, which we don't need to open, and we also have a contracts file. Now this contracts file has got nothing in it, right? So we're going to initialize that shortly, just after we finish installing stuff. Now this has a bit more to install than previously because it has to install .env. It also has to install Hardhat itself, plus a couple of other, Hardhat related packages. So that will take much longer than the previous npm installation. So we'll just wait for that to churn through. Or maybe while we're waiting for that, we can actually copy the Trogdor Solidity file into here. So where's that? Intro, copy, and then over here, paste. So now we've got a copy and we've got the original. Let's trash the original and rename this. All right. And it looks like the npm installation has succeeded. All right. So now we've got the completed smart contract inside of here. Let's switch over to hardhat.config.js and just sort of quickly go over what's inside of it. So what this does very critically is it needs an RPC URL. So that's where it's going to connect to this, and that's reading it from the .env file in the root of this folder that we set up right at the beginning, right? It also needs a seed phrase, which we also set up at the beginning. And it's going to use a derivation path plus the seed phrase, configure that to generate up to 10 accounts. I think that's the default, but if we need more, we can create more. But essentially right now, out of these 10, only the first 4 really do exist. Within Hardhat, we can configure what version Solidity you use. It's vital that that needs to be matching. That needs to match with the pragma that you specify inside of the files. So here we're going to use 0.8.17. All right. Next thing here is that we have to specify in different networks. So Hardhat always comes with a default set network configuration. So this is not a true network, so to speak. It's a emulated or simulated network that runs completely in memory. So it just basically is a fake, but it's very useful for testing because it doesn't require network hops. Transactions happen instantly at the rate, which is useful when you're testing. But then here is an instance of a real network. So that's the one that we'll be using, called Hedera testnet. And that uses the configuration for the accounts via the seed phrase, and it also uses the URL that we configured for the RPC that connects to this earlier on. So that's the brief sort of whirlwind tour of the Hardhat config file that has already been set up for you. Nothing really to do here. And we've already copied the smart contract while we're waiting for the npm install. Now let's check out a feature of Hardhat called a REPL, REPL, which stands for read evaluate. Now, this shell that I've been using here is ZSH that ships by default with Mac, and that is a form of REPL. But you can have tool or library or environment-specific REPLs, and that's what Hardhat provides. Hardhat's REPL is specific to connecting to a EVM-compatible network and interacting with it through RPCs predominantly, or through other APIs that Hardhat exposes. So that's what Hardhat's REPL is designed for. And in order to connect to what we're going to do is npx Hardhat, which will run the Hardhat version that has just been npm installed since it's present in the local directory. And then the subcommand is console, which is what it calls its REPL. And then we specify which network that we want to connect to. So your choices are essentially what's been specified inside the config. You can either choose Hardhat or Hedera testnet, and I'm going to use Hedera testnet, obviously. So this actually will connect to the Hedera testnet network, and you'll see that in the background, this thing will start churning through some output as and when I interact with it. So you'll also notice that previously, when I was using the shell, this was its prompt. That's what its prompt looked like. Now my prompt is this instead. This is one of the things that sort of signal that you're within the REPL. All right, and you can do .exit to exit it at any point in time, but we're just going to re-enter. Right. All right, so the first thing we're going to do is basically test that the network works. And we're going to get a block number. Now, Hedera doesn't, strictly speaking, have block numbers. It just has block numbers as a form of a RPC compatibility thing, but it's still a good way to sort of check whether we are live and getting the latest information from the network. It's kind of like a hello world when it comes to connecting to a EVM compatible network. So the syntax for this is slightly complex. Hopefully I get it all right. So await require, and then inside of it you want to call Hardhat. So this is basically the same as, I guess when you do it with npm installed, right? And then once we've got Hardhat, we do .network .provider .send, and then this basically allows us to send an RPC. And the RPC that we need is each get block by number. And then we want to send it some parameters of latest, I think. And if I get this wrong, I'll just copy paste it. The syntax is quite different to get exactly right. Yeah. And then we await this RPC response. Once we've got it, then we're only interested in the number value of it. Interesting. I'm just going to copy paste it then. Let's see if that works. All right. Yeah, I had a syntax error when typing it out manually. All right. So let's copy this number over here. And where are we? Trying to find my there we go. Window. All right. So convert. Yes. We got that. All right. Let's go to the Hedera Hashgraph. And where are the latest blocks? There we go. You can see over here, the latest block is 7732,000, and we've got 7732,000. So there we go. Now we'll repeat that command again and convert that again. You'll notice that, oops. Copy that. Let's do it one more time. And that's 052 and you can see 0.2 is here. So, there's one block approximately every 2 seconds. So you can see that it's increasing, and the number that we're getting when we query the RPC value over here is sort of following along in tandem with Hashgraph. So that's good. Awesome. So the next thing that we want to do is to check the address that we'll be using. So this one doesn't actually interact with the RPC at all. It's a far simpler one. So we want to do await hre.ethers.getSigners. And then we want to get the first one, and then we want to get the address. Did I do a typo? There we go. So that is 0x07ff, which is what we expected. It's the same one that we generated earlier on when we ran our generate EVM account script. Yeah, so you'll notice that this is not the same as an operator account. So the address of my operator account was 0x7394 something. And this is 0x07ff. And the difference is the operator account was the Hedera native account that we obtained from the Hedera portal, whereas this one is one of the EVM addresses that are generated using seed phrase. So, yeah. So let's actually run this a few times, but we will just change the property, right? 1 and 2. And each time we get a different set of addresses, and these are the ones that are all generated from the seed phrases. All right, so we've finished basically like doing our hello world for the REPL. We checked that we are indeed connected to the Hedera testnet network and validated some data on it. So let's exit the REPL. Now, the address that we've been using by default is this. So let's just check that on Hashscan. So let's just go to hashscan.io and then under testnet, search for that address, and we can see that this address has been funded. We're on our account page. We see the same EVM address. We see that it has a balance of HBAR, and this verifies that the account exists. Now, if you do the same steps and this says account doesn't exist or something to that effect, or if you come here and there's no balance, it's 0, then you will not be able to proceed with the rest of this tutorial. So you need to go back to previous steps and walk through them again, right? So now we're going to do the same sequence: compile, deploy, interact. But this time we'll be using Hardhat and EtherJS instead. That's going to be a bit simpler. npx Hardhat compile. Why did it say nothing to compile? Maybe I've done it earlier on. So let's go and delete the cache, delete the artifacts, right? All right, now let's tell it to compile again. I think it must have auto-compiled earlier. Okay, now it's just compiled one Solidity file directly, and it's recreated the cache and artifacts, which is what I wanted to see. All right, so firstly, let's take a look at the build cache, which is in the cache and Solidity files cache.json. So you'll see here there's some output basically saying a bunch of things that we expect, what the name of the smart contract is, what the version of Solidity is, etc., etc. The next thing is that if we open up the let's see, contracts, and then we see trogdor.json, we can find, okay, we've got its ABI over here, and we've got its bytecode over here. So this bytecode over here will be the output from the Solidity compiler, and this bytecode over here will be the output that we expect to see on Hashgraph. Now, what actually exists on network after this bytecode has been processed. And a more detailed explanation of that is available in the tutorial. Now, previously, in the Hedera SDK version of deployment, we use a contract create transaction. Now, Hardhat, EtherJS, etc., all the EVM tooling do not understand HAPIs at all. it's not possible to do a contract create transaction. Instead, what we'll be doing is something called an Ethereum transaction, which basically is defined in one of the HIPs, Hedera Improvement Proposal number 410. Go and check the full details of that. The link is provided in the tutorial. But essentially, every single transaction that is created via an EVM-compatible tool is an Ethereum transaction. And that Ethereum transaction basically is a wrapper around how EVM-compatible networks encode their transaction. So we will be deploying a transaction, but we'll be doing it in not only through a different tool, but also the underlying protocol level way that the contract is deployed is completely different as well. But end result is the same. We'll still have a deployed contract, with the exception of the EVM address not being a long zero address like we saw earlier on. Okay, let's see that in action. So let's again go back to the console. So npx Hardhat console, connect to the Hedera testnet network. Okay, and we're in. Now, what we're going to do is repeat the command that we did earlier on for getting the signers. But this time we're going to assign it to a variable. Deployer is equal to await HRE.ethers.get signers. I believe get signer. There we go. Then close that, then 0. Oops. Okay, so this will provide us with a signer with address object, and that's what we wanted. And then we need to create a contract factory, which is a step before the deployment specific to EtherJS. So let's just create Trogdor factory. Wait. HRE.get contract factory. And then we just need to refer to it by its name, right? All right, that worked. So how did that work? We didn't specify an ABI or an address or whatever. That's essentially because of the way Hardhat manages the compilation output. And we took a look at it earlier on in the artifacts and cache directory. So that's how it knew to find the relevant binary and the ABI and generate this contract object, as we see over here, a contract factory object, and from which we can use to create instances of a contract, in other words, deploy them, right? So that one's pretty simple. So we can just say Trogdor, right? So that's the actual contract itself. Trogdor is equal to await Trogdor factory dot. And we can see that sets off RPC activity over here in the RPC relay server that I've got running. And this will take a few seconds because deployment is a transaction and it's a fairly heavy one to process as well. But that's been completed, and now we have a contract. So this is the value of Trogdor now. All right. So what should we do next? We need to get a Trogdor deployment, right? So let's just do that. It is equal to await Trogdor deploy transaction and that's fairly instantaneous. It did have to make a network hop, but because the deployment had already completed, we got the results back pretty quick, right? And what we want is Trogdor deployment contract address. Essentially this property, right? This is what we're after. So now we're going to go over to Hashgraph, right, and search for that contract address, and we should find it, right? So this is the address it was deployed to, AB3F, and we've got it over here, AB3F. It's excellent. And we've got our contract bytecode. We only have one transaction on it, and that would have been the deployment transaction, right? So now let's interact with it. We're going to do the same set of interactions that we did before, but this time we're going to do it within the REPL instead of writing a script to interact with it. So we'll get more instantaneous feedback. Await functions dot min fee, and that should return us 100, right? Basically. Now let's do the same thing again, but instead of min fee, we want total burnt. Right, and that gives us a value 0 because we have yet to interact with it with any account, right? So now let's call the burninate function. So await dot functions dot burninate. Okay, so this function has no parameters, but in EtherJS, you can specify the way the API to specify it is an object at the end where we can specify things such as the payable value, right? So value of 1, 2, 3, right? So that, right, would be how you expect to send it in. However, what we actually need to do is we need to multiply this by 10 billion, right? And the reason for this, let me just make sure that I get the right number of zeros, right? It's because inside of the SDK.js tutorial, when we set the payable amount, it was just 123 tiny bars, right? And the SDK understands that natively. Now, when we go through the RPC, we're going through an EVM-compatible layer, right? And when we do that, right, we actually need to convert between tiny bar and something called waybar because it implicitly assumes, RPC implicitly assumes, because of the EVM specification, that the number of the tiniest unit is 10 to the power of minus 18, whereas a tiny bar is 10 to the power of minus 8, right? So that's where the 10 billion comes in, right? So you've got to multiply it by 10 billion or divide it by 10 billion, depending on whether you're sending a request or you're receiving a response, right? And full explanation for that is included in the tutorial text. So anyway, let's issue that command, right? And we'll send it a burninate. And we'll wait for that to churn. All right, it looks like it has completed the transaction, right? And let's press play over here. We should see an additional transaction. Let's click on that, and we can see that burninate has indeed happened, and the smart contract has been sent 123 tiny bars. Great, right? And yeah, just like before, we can see the logs as well, and we can see 123 in hexadecimal plus the address that it was sent from, 0x07FF, as we expect. All right, that's great. So what do we want to do next, right? So now we want to query min fee again. And we expect that to be the same because it's a constant. And we also want to query total burnt. So instead of seeing 0, like we did the first time, this time we will get 123. Right? Now let's also call, let's see, amounts, right? So in order to do that, we need to get account on the EVM address is equal to await HRE dot ethers dot get finance address. That should do it. So this is my account one EVM address. So now if I call amounts on it, right, I should get a value of 0. And yes, there we go. So let's change that to amounts, and then I will send in account one EVM address, and that should give me a value of 0. Now, if I get account 0 EVM address, let's just do that, right? Which is the one that, oh, what am I doing? I have sort of stuffed up this REPL. Account 1 EVM address was what I used earlier on. Account 0 this time, right? Dot address, right? So now I have an address, and now I'm going to invoke this with account 0 EVM address, and that's the one that I've been calling it with, and I expect to see 123 this time, which is what I get, right? So I've interacted with it, called burn innate, and then I've also called total burnt as well as amount and got the value of 123 with this specific account. But basically, now if we press play here, we won't see any more transactions because we actually haven't changed the state of the network. The last few things I've done have been interactions. Okay, I believe that's it for the interactive part of the workshop.